Here is our old friend, the common source amplifier. It is time to perform small signal analysis on it. This time, however, we have a much more comprehensive circuit. Let's introduce you to some of these quantities. First of all, notice the capacitor CC1. This is a coupling capacitor and is required to act as a perfect short circuit at all signal frequencies of interest while blocking DC. As we have discussed, the purpose of blocking DC is to make sure that the input signal does not interfere with the MOSFET's DC operating point. The other one, CC2, couples the voltage signal at the drain to the load resistance RL. Now RL can either be an actual load resistor to which the amplifier is required to provide its output voltage signal, or it can be the input resistance of another amplifier stage in cases where more than one stage of amplification is needed. We will study multi-stage amplifiers in the next course. CC2 also acts as a perfect short circuit at all signal frequencies of interest, and thus the output voltage V0 equals Vd. The third one, CS, is called a bypass capacitor. Its purpose is to provide such a low impedance that the current bypasses the output resistance of the current source I, and therefore a sure and certain signal ground is established. Otherwise, your value may be left floating. We'll study these in more detail. But now, we turn our attention to the equivalent circuit of the amplifier for small signal analysis. Hope you can see properly. We are going to perform a step-by-step small signal analysis on it, and you are urged to carefully observe each step. So we start from our left side. The input resistance Rin equals Rg. Remember how in the previous lesson we said that Rin was not equal to Rg? The reason was that the gate was connected to the drain. In this case, however, no such connection exists, and Rg is connected between gate and ground. That is why it is equal to Rin. Next we see Vi is given by this formula. This is a very simple voltage divider. We can put in the value of Rin and we get this expression. Now usually Rg is much larger tr sig. Remember that R sig is the internal resistance of the signal. And so Vi equals V sig. Agree? VGS is also equal to Vi. Look here. Yes? You can write an expression for V0. This is the current GMVGS multiplied by R0 parallel with RD parallel with RL, the effective resistance. Why is there a negative sign? Because GMVGS is flowing from V0 to the source. Using V0, we can find the voltage gain AV, and we introduce another quantity. This is the overall voltage gain. By overall, I mean that it is the gain from the signal source to the load. We can also write this as V0 over V sig. The expression comes out to be this one. R out, as you can see from the diagram, is the resistance looking into the drain. Now before we calculate that, we have to put V sig to 0. And then we look back into the output terminal as indicated. So our out comes out to be R0 parallel with RD. They are in parallel because they have two terminals in common, the drain and the ground. This is an example of a unilateral amplifier. That is, the input resistance does not depend on the load resistance. Similarly, their output resistance also does not depend on the value of the internal resistance of the signal source. The opposite of that is the non-unilateral amplifier. In this course, we are not going to be seeing them. We will, however, see them in later courses. Now, this is the complete small signal analysis. You should be able to do that for any circuit that you are given. The common source configuration is the most widely used of all MOSFET amplifier circuits. Others also exist, which we are going to be seeing in the next few lessons. However, whatever the configuration, you are expected to be able to perform the small signal analysis effectively. However, notice that this practice of making a separate diagram to accommodate the small signal equivalent model of the MOSFET is a bit time consuming. It is more useful to perform the small signal analysis directly on the circuit. Let me show you. Here, take a look at the main circuit. I have included Rn, Vi, Gm, VGS, VGS, and Rout, and also R0. Now remember that before we start our small signal analysis, we are to open our current sources and short our voltage sources. However, here I have left the voltage sources as they are, the DC voltage sources that is, and removed the capacitors and replaced them with short circuits and opened the only current source that was present. This analysis directly on the circuit saves a lot of time. So it's a good practice, and while you're encouraged to draw the separate small signal equivalent circuit model, you should also start practicing doing the analysis on the main circuit. That is going to save you a lot of time. Now let's move on to a modification of this circuit. This is our old circuit again. Now let me add a source resistance above the current source. Here it is, Rs. Obviously our small signal equivalent circuit will be a little changed. So let's draw that. Here you go. Notice where the gate, drain and source are. As you'll notice, this is not the hybrid pi model, but the T model. It is preferred to the pi model because it makes the analysis in this particular case very simple. Generally speaking, whenever a resistance is connected in the source lead, the T model is to be preferred. Why? Because the source resistance then simply appears in series with the resistance 1 over Gm, which represents the resistance between source and gate looking into the source. Notice that we have not included R0. In this particular case, R0 would have made the amplifier non-unilateral. However, the effect of R0 on the operation of this discrete circuit amplifier is not important. So we start our analysis again. Rn again equals Rg. We write the equation for Vi. However, Vi this time is not equal to VGS. Look here. VGS represents only part of Vi. So we can write this as VGS equals 1 over Gm divided by 1 over Gm plus Rs into Vi. You can clearly see that this is a voltage divider circuit. Rearranging, we find that the value of VGS is reduced by a factor 1 plus Gm Rs. However, Rs can be used to control the magnitude of the signal VGS. This ensures that VGS does not become too large, because it is essential for it to be kept small so that the small signal condition can be satisfied. There are other benefits of Rs, but we are not going to study them right now, but in later courses. The way Rs provides these benefits is through the process of negative feedback. We have touched upon that topic in one of the previous lessons. However, there is a price. Let's move forward. ID equals VI over 1 over Gm plus Rs. Do you agree? VI is the total voltage across the combined resistance of 1 over Gm and Rs, which are in series. And the current flowing through this combined resistance is I. Pretty straightforward. Moving on to V0, it is minus ID multiplied by RD parallel with RL. Again, the negative sign is because ID is flowing out of V0. We can plug in the value of ID and we get this expression on your bottom right. Now bringing VI to the left side gives us an expression for the voltage gain. The overall voltage gain GV can also be written as, comparing both these values, the one for the case where there was no resistance in the source lead indicates that including Rs results in a gain reduction by the factor 1 plus GMRS. This factor is called the amount of feedback. Because Rs reduces the gain, it is called source degeneration resistance.